In this video, we're going to prove the following theorem. There's going to be no longer a reason for you to just memorize it. The area of a circle with radius r is pi r squared. So that's what we want to prove. Now, before we go on to prove this, I want to say something that I'm sure you know. If you take this circle of radius r from the origin, centered at the origin, you take this circle and have that area, and maybe you move it over here. That is, this circle also have radius r. Well, this area is going to be the same as this area. Just because you move it, it's not going to change. If you have a checker piece, there's a checker piece, and it's solid. It has some area. Okay, it has some area. And now you move it. That's usually what you do with checker pieces. You move it. It looks like I made it a little bit bigger. I apologize for that. But when you move it here, the area is the same. It's not going to change. So, without loss of generality, I am going to find out the area of a circle, a radius r, that's centered at the origin. So, the equation of a circle of radius r centered at 0, 0 is x squared plus y squared equals r squared. Now, some more motivation. I want to find the area inside that circle, a radius r. So here's r, and here's y equals r, and x is negative r, and here y is negative r. Now, there one can argue, well, there's 4 pieces. You have this piece, you have that piece, you have that quarter piece, and you have this quarter piece. And it's reasonable to assume through this symmetry that each of those 4 pieces have the same area. In other words, one can find the area of just one of those pieces. For argument's sake, the one in the first quadrant. We can find the area of this, and then multiply it by 4, and then we would then get the area of the whole circle. So, the area is going to be 4 times the area of the circle is going to be 4 times the area of one of the quarters. So there's my 4 times. The area of the quarter, we're going to find a integral for that. So let's come down here again. Now, we know that x squared plus y squared equals r squared. And if I solve for y, by first solving for y squared, I bring this to the other side, and I get positive y squared is r squared minus x squared. So y must be plus or minus r squared minus x squared. Now remember, if what I just boxed is 9, then y equals 9. And if this is 22, then y equals 22. Y equals whatever this is. Now let's see. Now we only want that portion of the circle. Clearly, the y values are all positive because they're all above the x-axis. this y value is here, and this y value is what it says there, and this y value is what's marked on the y axis there and here, and here it can be 0, okay? But it's not negative. That is why I'm going to remove the negative. The equation of that line, that quarter circle is the square root of r squared minus x squared, where x goes from 0 to r. In fact, this whole thing is, the whole top half is y is always positive. We really have the constraint where x is at least 0. But we won't have to worry about really stating that, because our limits are never going to be less than 0. Because I guess we'll integrate with respect to x. Alright, so let's come back here. Let us draw what we have. We have this equation, this curve, where y is equal to the square root of x squared, r squared minus x squared. Right here is r, and for the record, right there is r. This is the y-axis, this is the x-axis. And we want to find the area in here. We want to find that area. The area bounded by the x-axis, the y-axis, and this curve. That's what we want. Then we'll multiply it by 4. Well, let's see how we're going to find this area. I choose to draw vertical strips. And since the base is delta x, and it's very, very small, on top, rather than saying that we have a little curve, we can almost call it straight. Because as delta x gets smaller and smaller, that curve really becomes straight or insignificant in the limit. And if we keep drawing these vertical strips, so those are dx's, we keep drawing them, well, what we see is they start when x is 0, and they finish in this one where x is r. And we have the base, it's the rectangle, base times height. Well, what's the height? How much is that height? Well, any height is the top minus the bottom. Well, the top is r squared minus x squared minus the bottom. Well, down here, along this whole line, y equals 0. So we get the top minus the 0, which is just the top. So this is the integral we're going to calculate for the top right corner, this corner of the circle, or that quarter of the circle. And we're going to multiply it by 4. So it's just a matter of evaluating this integral. Now, whenever you have r squared minus x squared, or x squared minus r squared, or x squared plus r squared, trig substitution. Make a triangle. And make this triangle. And when it comes to r squared minus x squared, the r squared is a positive term. So the square root of that always goes on the hypotenuse. And the negative term, x squared, the square root of that always goes on one of the legs. And the square root of that goes on the other leg. And if you verify this, when you square that, you get r squared minus x squared. And when you add back the x squared, you just get r squared. And that does equal to that square. And here's our angle u. Now, we want to rewrite everything here using u's. And need to find dx. Now, to find dx, it'd be really nice if I knew what x was. But whatever x equals, when I take the differential to the left side, I'll have dx equals the differential of the right side. That is, I'll have dx equals. That's my goal. So I look for the simplest trig function that involves x and say a number. And I realize the sine of u is opposite. So the sine of u is opposite over the hypotenuse, which is, basically a number, a constant. Now instead of dividing by r, I'll multiply the other side by r. So now I have what x equals, which is really good because now I can find dx. I take the differential of the left side and I compute the differential of the right side. And I now have what dx is. Now, in terms of u, I need to find out what r squared minus x squared is in terms of u. So I come back to my triangle and I see, well, that's what I want. I like to divide it by something that doesn't have x's. Oh, let me divide it by r. And I say, well, let's think. That's with respect to u, that's the adjacent, and that's the hypotenuse. And I say, aha, I have it. The cosine of u is the adjacent, which is square root of r squared minus x squared, divided by the hypotenuse, which is r. But I'll multiply the other side by r. The main reason is because I just want to know what this is. Same argument why I didn't divide the x by r. I only wanted to know what x is. So now we substitute back. We substitute. A is equal to 4 times the integral r square root of r squared minus x squared is r cosine u times dx, where dx is r cosine u du. Okay, and x is equal to r cosine theta. X is equal to r sine theta, excuse me. There's a reason why I'm writing this. R sine u. And the original limits were 0 to r. That is, x is 0 and x is r. Well, when x is 0, that is, when this is 0, I want that to be 0. And remember, see where our curve is. Remember that our angle is only going between 0 and pi over 2. First quadrant. Now, this here is the sine curve. And right here is pi. That is right here, pi over 2. And we're going from 0 to pi over 2. And I want to get 0. Because r times 0 will give me 0. And it seems that the cosine of 0 is 0. That is, if x is 0, u is 0. Now, I want x to be r. Well, if x is r, so this is r, then r is equal to r times something. If x is equal, x is r, x equals r sine of u. If x is r, so r is equal to r times something. That must be 1. R times 1 is r. And where is the sine of u1? Remember, so I'm going back to the sine graph. Remember, we're only in this portion. And it equals 1 right there. The highest point of a sine curve is 1. And it happens, look at that, at pi over 2. So u is pi over 2. So back to the limits here. The lower limit used to be x equals 0. Well, now u is 0. The upper limit used to be x is r. Well, that's when u is pi over 2. Okay, let's get rid of our side work here. Don't think we need much of this. So we just want to calculate this limit. So it equals this integral. 4 times the integral from 0 to pi over 2. R times R has nothing to do with U, which means I can factor out the R times R. The plus is R squared, and I'm left with cosine U times cosine U, du. When I looked at this for a couple of minutes or a couple of seconds, and I realized that I don't see any trig substitution, any U substitution that I can make. But I know that cosine squared U is equal to 1 plus cosine of 2x over 2. Okay, well, let me write U here. So I could substitute. This is equal to 4r squared from 0 to pi over 2 of cosine squared U, which I'm going to write that way, 1 plus cosine 2u over 2 times du. Okay. So let's clean this up a little bit. This 2 I can bring out in front, and of course 4r squared over 2 is 2r squared. This 2 goes into 4 2 times. And now I have the integral of 1 plus cosine 2u du from 0 to pi over 2. This is equal to 2r squared times, well, the integral of 1 du is u, plus the integral of cosine 2u du. Well, let's see a sine of u. Sorry, angle never changes. So it's going to be angle 2u. Now, the derivative of that is 2 cosine 2u. But we don't have the 2. We don't have the 2 here. So to get rid of the 2, I'm going to divide by 2. So this is the sine of 2u over u. Okay. So now, from 0 to pi over 2. Okay. So this is equal to 2r squared. U is pi over 2 plus the sine of 2 times pi over 2 over 2. Well, there's the over 2. 2 times pi over 2 is pi. You need to know your sine graph. Pi is right there. That's 0 plus 0. Minus, now I plug in u is 0. Well, if u is 0, that's 0 plus 2 times 0 is 0, and the sine of 0 is 0. So what's in the big brackets, 2r squared, well, this is 0, and take away 0, don't bother with, and pi over 2 plus 0 is pi over 2, and we are done. 2 goes into 2 evenly, and we're left with r squared times pi, better known as pi r squared. That is the area of the circle of pi r squared. Not because anyone told you, but because we proved it. Pretty neat.